So this is a walkthrough of the Electrons, Webs, and Photons paper from June 2014. I will try and keep an eye on the comments as they're coming through on my iPad while I'm working on this stream. Okay, so let's begin with question number 1. Excuse me one moment. I've now got my own voice coming back to me about a minute behind. That's better. Okay, right. Now we're ready to start. So question number 1, we've got figure 1.1. It's the IV characteristic of a 6-volt, 1.5 watt filament lamp. Part AI states how figure 1.1 shows that the filament lamp does not obey Ohm's law. Well, Ohm's law is when voltage is proportional to current, and in this case, voltage is not proportional to current. Part 2, explain how figure 1.1 shows that the resistance of the filament lamp is about 10 ohms when the current is between 0 and 50 milliamps. Well, if we look at this first section of the graph here, between up to around about there, at this point here, we're at 50 milliamps. And in that section of the graph, you can see it's almost a straight line. So we need to say that here. We need to say that V is approximately constant up to about 50 milliamps. This is the reason we have to say this, is because it's an explain question. It's not simply asking for a calculation. You need to explain why the calculation applies. This is one of the most common mistakes actually of this question, is that people missed out the explanation. So it's approximately constant up to about 50 milliamps, which means you can do the calculation. We know that that voltage equals current times resistance. So we'd rearrange that to get resistance equals voltage over current. Our voltage here, well, if we take the voltage when it is 50 milliamps, and the voltage there is about 0.5 volts. And the current is at 50 milliamps, so that's 50, be careful with the units, times 10 to the minus 3, sorry about that. So that comes out as 10 ohms. So you need both parts of this to get both marks. Explain why the resistance of the filament lamp is much larger, about 25 ohms at 6 volts. You can see if we look at the graph is flattening off. That means that for an increasing voltage, we're not getting as much of an increase in current, and that's due to the resistance getting larger. The reason for that is because as the temperature increases, the resistance increases, but that's not the full explanation. The reason the temperature is increasing is because the current is getting higher. So higher currents lead to increased temperatures. And part B, this was a really tricky question that certainly when we did this as a mock exam, not many students scored very highly in at all. If we look at the question, it's a potential divider circuit of sorts, but we can see here that part of the potential divider is a parallel combination of resistors, and that makes the question particularly tricky. It tells us that the LDR has a resistance of about 1 ohm when in daylight and about 1,000 ohms in the dark. And we need to show that the circuit will cause the lamp to be off during the day and on at night as long as the light from the lamp doesn't shine on the LDR. We should explain clearly with or without calculation how the circuit functions to cause the lamp to be off in daylight and on in the dark. So if I just zoom out a little bit so we can see the circuit. First thing to look at is in the light. So in the light, we need to consider the power. We can't look at this as a potential divider circuit straight away because we don't know what the combined resistance is here. We do, however, know that the resistance of this lamp, when the current's very low, we know from the first part of the question that it's 10 ohms. And when the voltage is much higher, so when the lamp's on, the resistance is increased to about 25 ohms. That's from the previous part of the question. We can remind you up here. It tells us that the resistance is about 25 ohms. So we can use both pieces of equipment there to see. So when it's in the light, the lamp's going to be switched off. So we should use the lower value of resistance. We need to work out the combination. We need to work out the resistance combination of the LDR and the light. So we need to use our resistors in parallel equation. That is 1 over R total equals 1 over R1 plus 1 over R2, and so on. We can shorten that to R equals, let's look first at our LDR here. We know that in the daylight it has a resistance of about 1 ohm, so 1 to the power of minus 1 plus, we said here we'd use 10 as our resistance when the lamp's switched off, 10 to the minus 1, close the bracket, and then take the reciprocal of all of that, take that to the minus 1, and that gives us a resistance for this combination of the two components here of 0.91 ohms. Now we can see by inspection actually that is much smaller than the 25 ohms, but we could do a potential divider calculation. I'm not going to work through it all, if only because the annotations aren't coming on very well here. But we can do the V out equals V in times R2 divided by R1 plus R2. We plug the numbers in, where this combination here is R2. That's the R2 of the potential divider. And this one here, 25 ohms, is the R1. That's our V in. And you end up with a V out of 0.42 volts. So the lamp would be switched off. That's not a high voltage at all relative to, considering it's a 12 volt lamp. So therefore, lamp is off. Now we can do a similar exercise in the dark. Again, calculating the combined resistance, and this time using 1,000 ohms as the resistance of the LDR because it's in the dark, and using 25 ohms as the resistance of the lamp because the lamp is now switched on, so it has a higher resistance, and that will produce a resistance of around 24 ohms. And once again, we can plug that into the potential divider equation. I will work through it this time. So V out equals 12, that's V in, multiplied by our R2 here, which is going to be the combination of LDR and lamp. In this case is 24 ohms, divided by the R1, which here is 25 ohms plus 24, and that will give us a voltage of 5.9 volts, which should be enough to turn on the lamp. So the lamp is on. Okay, on to question 2. I notice some of you seem to be having technical problems in the comments thread. If you could just read it. Sorry, I'm just reading through the technical problems. Is everyone on? Now, someone's asking where 24 has come from. The 24 there, if I just scroll back to that question, the 24 has come from doing R equals 1000 to the power of -1. That's because the LDR has a resistance of 1000 in the dark, plus 25 to the power of -1. 25 is the resistance of the lamp when it's switched on, according to the previous question. And if we take the reciprocal of that, that gives us 24. Sorry, I should perhaps have worked through the whole question. Okay, I'm conscious that that took a few minutes more than I'd like, so I'm going to push through a little bit faster than this. Question number 2, the electromotive, we're asked to link the units to various ones. It starts with electromotive force. So the trick with this kind of question is to look at what equations are suitable. For example, this one, you can try a few different equations for voltage, for electromotive force, but the one that's relevant this time is voltage equals work divided by charge. Now, the unit for work is a joule, the unit for charge is a coulomb. So that gives us this one. For resistance here, we know that resistance equals voltage divided by current. So we use this one, the volts per amp. Energy, work it's the same equation as above. Work is voltage times charge. So that's volt coulombs. And finally, charge, we know that Q equals IT. These are all formulae that you'll find on in your equation book. Q equals IT. The charge for that then is an amp times a second. Having a look at figure 2.1 here for part B. Define potential difference. So the definition for potential difference, remember you can get all the definitions you'll need from cowenphysics.com. The energy per unit charge transferred from electrical to other forms. Those other forms could be heat or light or whatever. And explain what is meant by internal resistance. Now, this was a tricky one, and the mark scheme for this is not all that helpful. But internal resistance, one way of describing it is that it's energy lost as heat in the battery. So the battery effectively has a resistance. The resistance has come as a result of the chemicals in the battery, and you can write things about that. But the mark scheme for this particular question was a bit strange. Okay, let's keep going. Explain why the current at X must be twice the current at Y or Z. If we just take a look back here, we know that the current at X is 0.16. We must need to say why the current at X is twice the current at Y or Z. Well, you can see here you have 6 ohms of resistance in this path and 12 ohms of resistance in this path. Both branches have got the same potential difference across it, whatever the terminal PD of this battery is. So we can say both branches have the same PD. Resistance in X is 6 ohms. Resistance in the YZ branch is 12 ohms. As I is equal to V over R, that means that I is inversely proportional to R. So current is inversely proportional to R. So current in X is double current in YZ. Calculate the potential difference across the 6 ohm resistor. So let's have a look at the 6 ohm resistor. It's up here, it's on the YZ branch. We know that the current in the YZ branch is half that of the X branch. So I equals 0. Amps. So V equals IR. Will give us 0.08 multiplied by 6. And that gives us an answer of 0.48 volts. Now, part 5 here, exceptionally tricky question. Not hugely difficult to understand, but quite difficult to put across in words. It suggests why the potential difference Vxz between X and Z is 0. So let's take a look back up here. You can see that in both cases, X and Z are in the middle numerically of their respective branches. So we've got 3 ohms to the left of X, 3 ohms to the right of X. We have 6 ohms to the left of Z, 6 ohms to the right of Z. So both of them are dividing their branch into 2. If the potential difference across the whole branch is the same across both branches, that follows that the potential difference across from X to this point here and from Z to this point here must also be equal. They have the same potential difference across the 6 ohm resistor as across the 3 ohm resistor. That means that actually there is, I think one way to think of it here is to think about the energy of the charges as they're flowing around. All of them will have this, they must have the same energy at this point as they would have at this point due to the potential difference across here. As I say, it's a difficult one to explain. One wording that should get marks on a question like this is that to acknowledge that the potential difference of the 3 ohm resistor is equal to the potential difference across the 6 ohm resistor. Therefore, charges at X and Z must both have equal energy. So the potential difference between these points is 0. Remember what the meaning of potential difference is. It's the difference between the energy of charges at two different points, and at these 2 points they have the same energy, so they have a 0 potential difference. Finally here, calculate the value of the internal resistance R. Well, we would use the equation here, E equals V plus I little r, where little r here represents the internal resistance, IR together, remember that's the lost volts. And we know that the potential difference across the 6 ohm resistor here is 0.48, and there's another 6 ohms here. So the total potential difference across the whole branch here, across the whole, remember parallel circuits, same potential difference across each branch. The total potential difference is going to be double this 0.48. So our voltage here will be 0. Oops. Remind me never to use Adobe for annotating these things again. 0.96 volts, and we can rearrange the equation first and then plug the values in. So we get I equals 0. It does not like decimal points. 16. I've skipped a step here. We also need to know the current, which we didn't previously know, but we do know what the current in one of the branches is. We know that the current in the X branch is 0.16, and we also worked out that the current is half that in the other branch, so the total current is 0.16. So the current out of the battery, 0.16 plus 0.08, and that gives us 0.24 amps. We can then rearrange our equation to get little r equals E minus V over I. We've plugged those values in. E here from the original diagram is 1.2. V is 0.96, as we've just worked out, and I is 0.24. It actually comes out with precisely 1.0 ohms as being our internal resistance. Okay, question number 3, define resistance. So resistance, the easiest way to define this answer this kind of question is to use a word equation. Remember, define in a question usually signals a word equation. So resistance equals voltage divided by current, and that would get you the mark. It's another tricky question in this paper here. The electrical section of this paper particularly was really quite tough, and as some of you have commented, the grade boundaries were relatively low for this exam paper. It gives us a conductor, and the conductor happens to be made of 20 atoms, a rectangle of 20 atoms along and 4 atoms across. And it tells us what the diameter of each of those atoms are. I wouldn't worry about the fact that they are spherical. We can make assumptions that the whole thing is a solid rectangle. So part I, show that the resistance between the ends P and Q of this block is greater than 200 ohms. The resistivity of phosphorus is 1.7 times 10 to the minus 8 ohm meters. So we need to use our equation here for resistivity, which is R equals rho L upon A. Rho is given to us in the question here, 1.7 times 10 to the minus 8. L, that's the length of the block, that's this dimension here. It's worth pointing out at this point that a mistake in terms of, in this kind of question, choosing the wrong dimension. So for example, doing height and width rather than length and width, or something like that. Especially when calculating a cross-sectional area, and a mistake in that, in which dimension to choose, would probably cost you marks for the whole question, because that would be classed by the examiner as incorrect physics. So you need to be really careful when you're selecting things like that. So our length here is d multiplied by 20, and we know that d is 3.8 times 10 to the minus 10 meters. So actually this comes out at 7.6 multiplied by 10 to the power of minus 9 meters. That's simply d times 20. Our cross-sectional area is going to be this dimension here multiplied by this dimension here. So the height versus the depth multiplied by the depth. So the height here is d. The width, or the depth, width is probably the best way of looking at it, is 4 times d. So we end up with 4d squared. Which comes out as 5.78 times 10 to the power of minus 19 meters squared. And then we can plug all of these into our equation here. So rho 1.7 times 10 to the minus 8, L 7.6 times 10 to the minus 9. Divide that by our d here, and it comes out as 224 ohms. Remember, this was a show that question, and indeed greater than 200 ohms. That sounds about right. Show that the number density of free electrons within the block is about 2 times 10 to the 28 meters per meter cubed. So that's saying that there are 2 times 10 to the 28 electrons in each cubic meter of this material. Assume that each phosphorus atom contributes 1 free electron. So the clue here is in this second part. So if every phosphorus atom contributes one free electron, then actually all it's asking us to work out is how many phosphorus atoms there are within this, each cubic meter of the block. If we know the volume of a phosphorus atom, and again, we're going to assume it to be a cube. If we know the volume of a phosphorus atom, that tells us how many meters cubed a phosphorus atom is. So we want to do the reciprocal of that. We want to do 1 over that. So the number density is going to be equal to 1 divided by the volume of a phosphorus atom, assuming it's a cube, which will be d cubed. And if we plug in the value for d, given here 3.8, it comes out as 1.82 times 10 to the power of 28 per meter cubed, which is again very similar to the question 2 times 10 to the 28. So a couple of show that questions there. This one, as long as you don't mess up which dimensions you're using and don't get confused by what is quite an abstract question, actually a relatively straightforward application of the R equals rho L over A. And this one, perhaps not a difficult calculation, but a little harder to understand why you would be doing that. But if the volume here is the number of meters cubed per atom, then what we want to find is the number of atoms per meter cubed. So we just do the reciprocal. Calculate the current between P and Q when the mean drift velocity of free electrons in the block is 1.9 times 10 to the minus 5 meters. The equation here, the clue for which equation to select is right here, the mean drift velocity. We only have one equation that uses the mean drift velocity, and that is I equals A little n little e little v, where v there is the mean drift velocity. We don't need to rearrange anything, and we have all the information we need. A is our cross-sectional area that we worked out up here. It was a good job we wrote it down, 5.78 times 10 to the minus 19. N is, or we can use 2 times 10 to the 28, or we can use our calculated value there, which is 1.82 times 10 to the power of 28. Our E is the charge of an electron. This is on your formula sheet if you can't remember it. It's 1.6 times 10 to the minus 19. And finally, our velocity given to us in the question here is 1.9 times 10 to the minus 5. Oops. And that gives us an answer of 3.2. Times 10 to the minus 14. And part 4, there are about 10 to the power of 9 of these tiny conductors in a single chip, each carrying the current calculated in part 3. Estimate the total power dissipated in these conductors in a single chip. So let's first of all work out what the power dissipated in one of these tiny conductors. Apologies again for my inability to draw dots for some reason in Adobe Acrobat. So we've got 3 equations for power dissipation. We've got P equals IV, P equals I squared R, and P equals V squared over R. They're all on your formula sheet. On this occasion, we know the current and we know the resistance. So it's appropriate to use P equals I squared R. Where I is going to be our calculated value here, 3.2 times 10 to the minus 14. And R is our resistance that we calculated here, 224 ohms. Lots of opportunities for errors to be carried forward here, by the way. It's a very difficult question, but there are show that elements right throughout it. So even if you can't do these earlier parts, you can still apply it to this part, or even, and this is a general tip for exams as well. If you really can't do a question, guess, write down an answer, because if the subsequent part of the question relies on that previous answer, if you've written an answer down, the examiner can carry that error forward. If you just make up a value in the next part of the question, the examiner can't carry it forward. It needs to be written in the previous part, in the part that it applied to. So we can plug in our values here for current and resistance, and we will end up with a power per conductor of 2.29 times 10 to the power of minus 25 watts. And now we need to multiply that. So multiply that by 10 to the power of 29, sorry, 10 to the power of 9. Which will give us a total power consumption of 2.29 times 10 to the minus 16. And the final part of this quite long question, a little bit more accessible, I think, than some of the earlier parts. It takes about 4 times 10 to the minus 4 seconds for an electron to pass from P to Q. But the electrical signal, which is an electromagnetic wave, is transmitted across the block in about 3 times 10 to the minus 17 seconds. Explain why these times are so different. Well, electrons travel at a mean drift velocity is much, much slower than the signal, travels at the speed of light. It's as simple as that. The electrons travel a lot slower than the signal. The signal is an electromagnetic wave. That's the big clue in the question there. Travels at the speed of light. Okay, onwards to question number 4 here, which is actually a mixture between electricity and photons. So we can see the IV characteristic for a blue light emitting diode. And it's given us the circuit as well. So A part I says the data for plotting the IV characteristic is collected using the components shown in figure 4.2. That's the circuit diagram here. By drawing on figure 4.2, complete the circuit showing how you would connect the 2 meters needed to collect these data. So an IV characteristic is current and voltage. So obviously we need to measure the current and the voltage. We measure the current with an ammeter. Ammeters are always connected in series. So we can stick that in there. And the voltmeter is always connected in parallel. A common mistake, I think, in this question is to connect the voltmeter across the wrong component. We are only interested in the voltage across the LED. If we were to connect it across both, all that would tell us is the voltage of the power supply. So we are just going to connect our voltmeter right here across the LED. And that would get you the 1 mark. When the current in the circuit of figure 4.2 is 20 milliamps, calculate the terminal potential difference across the supply. So this is it's sort of a potential divider, isn't it? Or you can look at it in terms of Kirchhoff's second law. The potential difference across the supply here, this potential difference across the whole supply, is going to be is going to be equal to the potential difference across the 100 ohm resistor and the potential difference across the LED. So terminal PD equals the voltage across the fixed resistor plus the voltage across the LED. So the voltage across the resistor is going to be at we know the current is 20 milliamps and we know the resistance is 100, so V equals IR. So 20 milliamps is 20 times 10 to the minus 3. Again, this is another example of where we need to be really careful checking units. Always, when you look reading graphs, look at the units on the axes, because often it's very rare that current is measured in whole amps, because an amp is quite a significant amount. So in electronics, you'd usually be working in milliamps, and we need to reflect that in our calculations. So 20 times 10 to the minus 3 multiplied by 100 ohms gives us 2 volts. So that's the voltage, that's the potential difference across the resistor. That's not all that we need, though. We also need the potential difference across the LED, and for that we can read off the graph. So we can look here at 20 milliamps, read across, and it's this corner here, read down is 4 volts. So V LED equals 4 volts. Combine those two together and we get 6.0 volts. Remember, OCR insist on answers being put to 2 or 3 significant figures. The mark scheme generally refers to 2 significant figures. In a question like this, you wouldn't lose a mark if you just wrote down 6, but it's good practice to write down 6.0. The energy of each photon emitted by the LED comes from an electron passing through the LED. The energy of each blue photon emitted by the LED is 4.1 times 10 to the power of minus 19 joules. Calculate the energy of a blue photon in electron volts. Just responding to a question actually in the comments, presumably regarding this question here. Yes, you can do it as a potential divider. in that circumstance, you would use the graph here. You divide voltage by current to work out the resistance of the LED, and then you could work backwards from the voltage here of 4 volts and use the potential divider equation to find out what the input voltage is. That's an alternative route to getting the same answer here. So calculate the energy of a blue photon in electron volts. They've given us the energy in joules. We need to convert that to electron volts. So it's a unit conversion question. If we want to convert joules to electron volts, we need to divide the joules, 4.1 times 10 to the minus 19, by 1.6, the charge on an electron, which is, 1.6 times 10 to the minus 19, which is the conversion factor. One electron volt is 1.6 times 10 to the minus 19 joules. So doing this division here, and that gives us 2.56 or 2.6 electron volts. Part 2, explain how your answer to I is related to the shape of the curve in figure 4.1. Well, if we take a look up at our graph here, we can see that 2.6 is actually the point where the LED begins to conduct. Up to that point, the LED has infinite resistance. There's no current flowing through it. So we should write something about this. So the LED only conducts above 2.6 volts. What this means is that an electron requires at least 2.6 volts in order, so that's the energy you'd give to each electron, 2.6 joules per coulomb, 2.6 volts, in order to release energy as a photon. Minimum energy required. After that brief look at photon science, let's have a look back, consider some electrons again. So calculate for a current of 20 milliamps the number n of electrons passing through the LED per second. So 20 milliamps, that tells us, remember that charge is, current is charge per second. So 20 milliamps just means 20 millicoulombs per second. So if we know how many, if we know that's 20 times 10 to the minus 3 coulombs per second, and we know how many coulombs an electron is, we can divide one by the other to work out the number of electrons per second. This is the kind of question where it's very easy to divide and multiply by the wrong thing. And to be honest, if you're not certain whether you're dividing one thing by the other or multiplying them, try it a couple of ways and sanity check the answer. You should get a huge number here, an enormous number. It's the number of electrons flowing through an electron. Electrons are tiny, so it should be an enormous number. So let's try here. N equals 20 times 10 to the minus 3, which is our coulombs flowing every second. Divide that by the charge on one electron, which is 1.6 times 10 to the minus 19. Another way of approaching this, by the way, is to think about the units. So we are looking for something in the units of per second, aren't we? Because we're interested in the number of electrons flowing per second. So that should be equal to, in this case, 20 times 10 to the minus 3 coulombs per second, divided by 1.6 times 10 to the minus 19 coulombs, and you can see those would cancel, and that would give us our seconds to the minus 1 on both sides. So that's just a way of sanity checking the equation we've done there. Another way is to look at the answer, and the answer here is 1.25, 1.3 times 10 to the power of 17 electrons per second, which is a very sensible number. It's huge. The total energy of the light emitted per second. So we know the energy per photon is 4.1 times 10 to the minus 19. We know that each photon is caused by one electron. So we know that there are this many electrons passing through each second. So it follows that there should also be that number of photons being released every second. So we just need to multiply together the number of photons being released every second by the energy of each of those photons, and you'll end up with 1.3 times 10 to the 17 multiplied by 4.1 times 10 to the power of minus 19. And that gives us 0.0513. And the final part of this little bit here, part 3, the efficiency of the LED in transforming electrical energy into light energy. So we know how much energy is coming out per second in watts, joules per second, 0.0513. We need to know how much energy went into that. And to do that, we're going to need to use some electrical equations. We've got our 3 equations: P equals IV, P equals I squared R, P equals V squared divided by R. On this occasion, we know the current flowing through is 20 times 10 to the minus 3. And we know that there's a PD across it of 4 volts. So we can do P equals IV equals 20 times 10 to the minus 3 multiplied by 4. And that gives us 0.08 watts. And we're looking for the efficiency. So efficiency is, you find this on the formula sheet, it's the useful output energy divided by the input energy. In this case, the useful output energy, the light energy, 0.05, excuse me, 1.3, apologies for the handwriting there, divided by 0.08. And that will give us 0.64 as our efficiency, or 64% if you prefer. And the last part here, the energy of a photon emitted by a red LED is 2 electron volts. The current in this LED is 20 milliamps when the PD across it is 3.4 volts. Draw the IV characteristic of this LED on figure 4.1. So scrolling back up to figure 4.1, the first thing it tells us is that at 3.4 volts, the current is 20 milliamps. So we have a point here. It also tells us that the, if we scroll back down to the question here, it tells us that the energy of a photon emitted by it is 2 electron volts. So that is going to be equivalent to the point on the axis that it leaves the axis here. So you're going to end up with a line, and apologies for this inevitably poor quality sketch, but it will go up like this. It should be a straight line for the most part, with a slight curve at the bottom passing through this point here. Just pause a second to see if there's any questions to catch up on. Okay, on to question number 5, and a waves question now. A little break from electricity. So we've shown an experiment here. We've got 2 loudspeakers connected to a signal generator, emitting sound at a single frequency but with different amplitudes. A person walks in the direction from O to Q, so walking along this line here, and they're noticing, well, they'll notice a change in the amplitude of the sound. We'll come to that in a second. And that's the distance there. The sound wave emitted individually by S and T have displacements x, s, and x, t at the point P. The graphs here show the variation. The amplitude of the wave from T is twice that of the wave from S. That's generous of us to tell us that. We should be able to see that from the graph. We can see that the wave from S has an amplitude of 2 and the wave from T has an amplitude of 4 micrometers. First part here, explain whether or not the 2 waves are coherent. Well, the definition of a coherent wave is one that has a constant path difference. Characteristics of that, I mean, if it's got a constant path difference, it will also have a constant frequency. The same frequency. The 2 waves will have the same frequency. The way to spot that is, do the 2 waves become out of line with each other? And you can see they don't here. The peaks and the troughs match up. It's perfectly out of phase with each other. There's a constant phase difference. Some students, when answering this question, wrote down that they are not coherent because they're out of phase. That's not true. A coherent wave can be out of phase. It just has a constant phase difference, in this case, of 180 degrees. So yes, they are coherent because they have a constant phase difference. Explain why the sound heard at P will be of a minimum but not 0 intensity. So these are the graphs measured at the point at P, and you can see they are perfectly out of phase with each other at point P. So the first thing we need to do is explain why there will be a minimum. Well, the 2 waves are in antiphase. If that's a word you've not come across before, it just means that the waves are 180 degrees out of phase with each other. We have one wave will have a peak when the other wave has a trough. So there will be a minimum. This minimum is not 0 because there is a resultant amplitude, and I'll show you what I mean by that. We look back at this wave here. Let's take this point A. Wave F meters. Wave T has an amplitude of -4 micrometers. So if we sum those together, the resultant wave would have an amplitude of -2 here. So the 2 waves don't perfectly cancel each other out. So there's a resultant amplitude, and that means there's a minimum. There will still be sound there, but it won't be 0. State the phase difference between the oscillation at time A labeled on the t-axis. So A to B, the first part asks for. Well, one whole wave here from 0 to 0.8 is 360 degrees. From 0 to 0.4 is half a wave. That's going to be 180 degrees. And this from A to B here is half of that, so a quarter of a wave, which is 90 degrees. And from A to C, we've got 90 degrees plus an eighth of a wave. So that's going to be another 45 degrees there. So in total, A to C there is 135 degrees. A common mistake here actually was students failing to write the degree symbol, and that cost a mark. And the reason for that is because you can answer this in radians if you really want to. So make sure you're careful with this and label the units. DI, calculate the wavelength lambda of the sound waves emitted from the loudspeakers. So here we need to use our wave equation, V equals F lambda. Often when we're using this equation, V will be the speed of light, but on this occasion we're talking about sound, not light. So it is this 340 meters per second. We don't know F. We want to find lambda. We don't know F, so we can find F by using the other equation here. F equals 1 divided by T. And our time period, if we just whiz back up here, the time period for one complete wave from 0 to 0.8. So that's 0.8, and that's in milliseconds, the axis on this graph. So 0.8 times 10 to the minus 3. Sorry, that should be the reciprocal of this. And that will give us a frequency then of 1250 hertz, which we can plug back into the equation then. So lambda equals V divided by F, 340 divided by 1250, and that gives us 0.272 meters. Excuse me. Oh. You get the idea. That's supposed to be an M. The final point here, maximum intensity of sound is at point O. The loudspeakers are 0.4 meters apart, and the distance OP is 2.4 meters. P is the position of the first minute. I'm just going to zoom out so we can try and, if I can view. That's not much good. So the loudspeakers are 0.4 meters apart, and the distance between O and P is 2.4 meters. P is the position of the first minimum. That's a really important point. We need to calculate the distance D. We can assume that the equation used for the interference of light from a double slit also applies to the sound from these two loudspeakers. So really what looks like an experiment that you've not come across before, you may not be overly familiar with, is actually one of the kind of the standard experiments you should know about, the Young double slit experiment for light. So the equation for that on your formula sheet is lambda equals AX divided by capital D, where A here is the separation of the loudspeakers. That's the slit separation in the Young double slit experiment. But here we've got two separate sources instead of two slits, and that's 0.4. X is the distance between the fringes in a Young double slit experiment. Now let's just take a look at our diagram here. A very common mistake in this question would be to say that the fringes would be at O and P and that the distance is 2.4. That's not the case. P is a minimum. That's a dark between two bright fringes. If this was a light experiment, or between two maxima, will be from O to Q. So that's going to be 4.8, 2.4, 4.8. And we have our wavelength from the previous question. So we can rearrange this. We use D equals AX divided by lambda, and we plug in our values here, 0.4, 4.8 and 0.272, and it will give us a distance between the speakers and the listener of 7.1 meters. Okay, on to the next question. Sorry, the next part of this question, quite a long question. Explain the term intensity. Definition of intensity is power per unit area. That. Okay, in part 2, the intensity of the sound at point P, the minimum, is 4 times 10 to the minus 6 watts per square meter. Use data from figure 5.2 to calculate the maximum intensity of sound at point O. So let's have a look back at figure 5.2 since it tells us that's so important. And let's take a look at the amplitudes of these waves. You can see the amplitude, the maximum displacement from the equilibrium position, the amplitude of wave S is 2 micrometers. And the amplitude of wave T is 4 micrometers. So we need to consider what will happen when those waves interfere destructively and constructively. So when they're interfering constructively, for example, at point O, the amplitude is going to be equal to the sum of the two amplitudes, the two maximum points, because we're adding those two graphs. That remember that those two graphs, as you see them there, are only true at point P, at the minimum. So they'll when they're at point O, the two waves are arriving in phase with each other, so they will interfere constructively. So the amplitude here is going to be 2 plus 4, so obviously 6 micrometers. And at point P, the amplitude is going to be 4 take away 2, because this time we are destructively interfering. We have one wave cancelling out partially the other one, and you end up with a net amplitude of 2. So you'll see here that the ratio between these two numbers is 3 times. However, intensity is proportional to amplitude squared. So the ratio between the intensity at point O and the intensity at point P will not be 3 times, it will be 3 squared, or 9 times. So our answer will be 4.0 times 10 to the minus 6 multiplied by 3 squared, or 9, and that will give us a maximum intensity of 3.6 times 10 to the power of minus 5. Question number 6 is a waves question, mostly about polarization. States 2 properties which distinguish electromagnetic waves from other transverse waves. This is the kind of question you want to look forward to in an exam paper. Okay, there's about 3 possible answers you can write down. They're not hugely difficult to remember. Electromagnetic waves light, for example, compared to other transverse waves. So we can say that electromagnetic waves travel at the speed of light, the only thing that does, and electromagnetic waves travel in a vacuum. That will do. That will get us 2 marks. E part I, describe what is meant by a plane polarized wave. There's a couple of marks here, so it relies perhaps a bit more detail than a simple definition. So it's worth saying that the oscillations wave are in one direction, or one plane is better to say. The mark scheme actually says direction, but are in one plane only. That plane is perpendicular to the direction of travel of the wave. Now, that's the second part of the definition there is really sort of just the definition for a transverse wave. You can only polarize a transverse wave. It's impossible to polarize a longitudinal wave. Right, part 2, and especially part 3. Well, part 2 is not too bad. Part 3 is a very tricky question. Explain. We have a situation here where we have 2 polarizing filters, 2 Polaroids at 90 degrees to each other. And we need to explain why the lamp cannot be seen by the eye. So we need to describe step by step what's happening. So after passing through polarizer 1, light is vertically polarized. Only horizontally polarized light is able to pass through Polaroid 2. Therefore, no light reaches the eye. The marks there, 1 mark for each line. Not too bad if you understand polarization. It's just a matter of being very clear in your answer there. It's worth bearing in mind the mark scheme requires you to use words such as vertically and horizontally, or words to that effect. Clarity is all important there. Part 3, very strange phenomenon, and one that perhaps is counterintuitive. But you have the same 2 Polaroids, and this time you put a third Polaroid in the middle, this one at an angle of 45 degrees to the other 2. Explain whether or not any light reaches the eye through the 3 filters. Common sense would tell us that if light can't get through 2 and 1, then there's no way it should be able to get through 2, 3, and 1. However, that's not actually the case, and I'll do my best to explain why that is. The horizontally polarized, the vertically polarized light passing through 1 has a component in the direction, in the plane, let's say direction, in the direction of polarizer 3. In other words, this is it's thinking about vectors from mechanics, and thinking about components. So this has a component. The one is at 45 degrees to the other, so there is a component in the direction of polarizer 3. Therefore, some light is able to pass through polarizer 3. Then you have the light approaching, a small amount of light approaching diagonally polarized. It reaches polarizer 2, and it has a component again at 45 degrees. The two are at 45 degrees to each other, and it has a component in the horizontal direction. So some light is able to pass through, and it really is quite counterintuitive, because you would look at non-pass-through polarized at 1 and 2, but by adding a third one at an angle, it is able to allow some to pass through. You can use Marlus's law here, by the way. I'm not going to go into detail about that, but you could use Marlus's law to show that to show numerically why some light is able to pass through through all three filters. Okay, just to respond to one or two of the questions, you can see I've got about 2 more questions to go. If technology allows, I will try and answer any more questions at the end as well. And also in response to Bergkamp 49, your guess is as good as mine. I have no idea what's going to come up after the mechanics paper, which was pretty unpredictable. I'm not sure. I would, given the lack of definitions on the mechanics paper, I would make sure you're good at the definitions for this one, especially sort of the ones related to waves. They often come up, and things like defining EMF and Kirchhoff's laws. They weren't in last year's paper, but it's really a mug's game to try and predict what OCR are going to do. So I'm sorry. Okay, question number 7. This is an experiment that if you're one of my students, we actually did this with some cheese on toast in class, I think before Christmas. You can estimate the speed of electromagnetic waves using hotspots inside the microwave oven. Microwaves are emitted in all directions, and that's the frequency, and stationary waves are set up. And this shows a typical pattern of the center of the hotspots marked X. You can try this for yourself. Take the spinning plate out of your microwave, put in a slice of bread with some cheese on top, and you'll see hotspots forming. And those are the due to the standing waves that are set up in the microwave. But maybe not tonight. Do that tomorrow after your exam. And from that, you can calculate the speed of light. It's a wild evening in. So explain how the stationary microwave pattern is set up in the oven. Well, microwaves are reflected off the walls. The reflected waves interfere or superpose with the incident waves. This produces nodes and antinodes. It's really not clear why they gave you so much space for that for 3 marks. That's all you need to write, and that will get you the 3 marks for that part of the question. Explain whether the points marked X on figure 7.1 are at nodes or antinodes in the wave pattern. Remember, the points marked X represent, where does it say this? It represent the hot spots. Okay, that's where the chocolate or the cheese would melt the most. So it makes sense that these are the places where there is the most energy. So that's not going to be a node. Remember, a node is where the wave there's actually no oscillation at all, because it's fixed. So the antinode is where we have the maximum oscillation. That's going to be where there's the most energy. So the X are antinodes, because this is where there is the most energy. Sorry, the maximum energy. Figure 7.1 has been drawn to half scale by using measurements taken from the diagram. Make an estimate of the speed c of the microwaves. Make your reasoning clear. By the way, this if you've done this as a mock exam, this would have been the scaling goes off because you'll see from the real papers they shrink A4s down slightly. So when you do the real exam, things work to scale. When you do it on paper, it doesn't. So don't worry if you tried this question before and found that your measurements were off. That's OCR's fault when they converted it to a PDF from the original exam paper. So it's drawn to half scale by using measurements taken from the diagram. Make an estimate of the speed c of the microwaves. Make your reasoning clear. Well, we need to measure the distance from antinode to antinode. And you can measure that from the diagram and then scale it, and that gives you 6 centimeters. I think on the diagram it comes out as 3 and you have to double it. Remember though, the gap from antinode to antinode is not 1 wavelength, it is only half a wavelength, lambda over 2, which means that our wavelength here for our wave is 12 centimeters. We can now use v equals f lambda to work out the speed of light. We know what to expect here. The frequency given to us in the question, the top of the question, is 2.5 times 10 to the power of 9 hertz, and multiplied by our wavelength of 12 centimeters, which is 12 times 10 to the minus 2, or 0.12. And that will give us an answer, as we'd expect, of 3 times 10 to the power of 8. Just to fill you in a little bit on the mark scheme for this, you would get a mark, I believe, for this part. This is kind of a method mark here, which you would score whether or not you wrote it down, as long as you subsequently got the right answer. A mark for this, and then a mark for this. You're not going to get a mark if you can't do the rest of it. You're not going to get a mark just for writing down the speed of light. That hinges on you doing the correct calculation. So there are 4 marks available here. Just to repeat what Cheyenne's written in the comments, if you are wanting to practice definitions, I can't tell you whether or not there's going to be loads of definitions in this exam, but it's worth knowing them. You go on cowenphysics.com. There are links to Quizlet, which is an excellent way of practicing some of the definitions. All of the definitions there are from me having trolled through past paper mark schemes and the specification to find kind of OCR's definitive definitions. So they should all work for you in the exam. Question number 8 is about the photoelectric effect. 440 nanometer light is incident on a clean metal surface and it causes electrons to be emitted, but no electrons are emitted when the wavelength is greater than 550 nanometers. Define the term work function. So the work function is the minimum energy required for an electron to escape from the surface of a metal. It's crucial that you state that it's a metal surface, the surface of a metal, not the metal in overall. You would lose the mark if you didn't say surface. Equally, you would lose a mark if you didn't say minimum as well. And explain how the work function is related to the threshold frequency. Well, the work function is the minimum energy required. The threshold frequency is the minimum frequency required. So a photon with less than the threshold frequency cannot cause electron emission. You could write the equation here. I haven't got a symbol for phi, so I'm just going to write work function equals h, Planck constant, multiplied by the threshold frequency. Right. You should write it out in words. If you wrote it out in symbols, you'd have to define the symbols. That's pretty much always the case in any written question. Let's calculate the value for the work function here. Well, we know that we haven't been given the threshold frequency. We do, however, know, if you like, the threshold wavelength, the minimum, the maximum wavelength that will allow electrons to be emitted from the surface. So we can use the equation work function equals hc divided by lambda, and that's going to be equal to 6.63 times 10 to the minus 34, which is the Planck constant on your formula sheet, 3 times 10 to the 8, which is the speed of light on your formula sheet. So hc, I'm not going to write those out in full, divided by lambda here, which is 550 nanometers. Nano is times 10 to the power of minus 9. That might be a bit of knowledge from your mechanics paper, but it's one that you absolutely still need to know. The answer here is 3.6 times 10 to the minus 19. It's worth, as another little tip for sanity checking these kind of answers, work functions and that sort of thing are usually going to be in the region of 10 to the minus 19, 10 to the minus 18, around about there. So if you've got a positive power here or a very small negative power, you're off somewhere. Something's gone wrong. B part I, show that the maximum speed of the emitted electrons in the experiment is about 4.5 times 10 to the power of 5 meters per second. Quite a long-winded question, this one, and it's worth 3 marks. We do know that HF equals our work function plus the maximum kinetic energy of the emitted electrons. So that's Ke max. Oops. But we don't know F. We know, however, that hc over lambda is the same as hf. So we can say that hc over lambda equals phi work function plus Ke max. And we can rearrange this and we'll end up with Ke max equals hc over lambda minus the work function. And we can, again, I'm not going to write out h and c, they're constants from your formula sheet. So hc divided by, and this time we are interested in the other wavelength. So when we were working out the work function, we're interested in that maximum wavelength, the maximum wavelength, because that's the equivalent to the threshold frequency. But here we're interested in the actual experiment, which is using 440 nanometer light. So we need to divide that by 440 times 10 to the power of minus 9. And take away the work function we worked out up here, which is 3.6 times 10 to the minus 19. And that gives us a kinetic energy of 9.2 times 10 to the minus 20. That's not the final answer though. We need to find V, so we can rearrange our Ke equals half mv squared. We'll end up with v is the square root of 2ke divided by m. Now, what's m here? Well, m is the mass of an electron, which is on your formula sheet. That's 9.1 times 10 to the minus 31. So we can plug in 2 multiplied by this number here, the kinetic energy, divided by 9.1 times 10 to the minus 31. Remember to take the square root of it. And at the end of all that, you end up with 4.45 times 10 to the power of 5. Which is, as it's a show that question, yeah, pretty much spot on. Part 2, calculate the minimum de Broglie wavelength of an emitted electron. The equation for a de Broglie wavelength, again on your formula sheet, lambda equals, h divided by mv. So the Planck constant divided by momentum. We know the Planck constant, 6.63 times 10 to the minus 34. Divide that by the mass of an electron, 9.1 times 10 to the minus 31. And multiplied by our speed that we've just got in the previous part, 4.5. Times 10 to the power of 5. And you end up with a de Broglie wavelength that comes out as 1.6 times 10 to the minus 9 meters. So that's the effective wavelength of the electron that's been emitted. And the very, very last part of this exam paper then is part C here, which is on line spectra. So the light source of the experiment is a discharge lamp containing excited atoms which emits light at several wavelengths. Figure 8.1 shows the 3 lowest energy levels of one of these atoms, N1, N2, and N3. Electron transitions between these energy levels can produce 3 different wavelengths of radiation. The transition between n equals 2 and n equals 1 causes the 440 nanometer photons. Be really careful with this question because students tend to get the relationship between energy and wavelength the wrong way around. Remember the equation, E equals hc over lambda. H and c are constant, so E is proportional to 1 over lambda, which means that if we want more energy, we need a shorter wavelength. So we know that between N2 and N1, this gap here, we have 440 nanometer photons. So if we want a gap of 590 nanometers, it can't possibly be, there's only 2 possible other routes, N3 to N2 or N3 to N1. It can't be the largest of those because a 590 nanometer photon has less energy than a 440 nanometer photon. So it must be the smaller gap here, which is from N3 to N2. Just a point from the mark scheme on that. It's really important that you say 3 to 2, that you draw an arrow going from 3 to 2. If you just wrote down 3 and 2, you wouldn't get the mark because it's got to be clear which direction the electron is traveling in order to cause the photon to be released. Finally, calculate the wavelength of the photons emitted by the 3rd transition. Okay, so we've got 3 transitions here, 3 to 2, 2 to 1, and 3 to 1. The 3rd transition we're interested in is E3, that's a 3 to 1. And that's going to be equal to the energy of 3 to 2. That's a 2, believe it or not, plus the energy from 2 to 1. And you know in each of these cases that E equals hc over lambda. So hc over lambda 3 to 1 equals hc over lambda 3 to 2 plus hc over lambda 2 to 1. Our hc's can all cancel. We divide the whole lot by hc, which means that we're left with 1 over lambda 3 to 1 equals 1 over lambda 3 to 2 plus 1 over lambda 2 to 1. And we can now plug some values into this. So 1 over 590 nanometers. We can actually leave it as nanometers here and convert it at the end. 1 over 590 nanometers plus 1 over 440 nanometers equals 1 over lambda 3 to 1, which is what we're interested in. So we add those together, we take the reciprocal, and we find that lambda 3 to 1 equals 252 nanometers. This one's in meters, so 252 times 10 to the minus 9. And that is electrons, waves, and photons. And we did it in less than an hour and 45. But it was a hard paper. Okay, if anybody has any more questions, I'll have a quick look through the comments. If anybody has any more questions, feel free to add them in. Okay, yeah, just to answer Sunil Kumar, can you go through another paper? As somebody else has pointed out, I'm not going to be able to go through another one now. However, the whole of the June 2013 one is on this YouTube channel, broken down by questions. Feel free to work your way through those. Legend Footy says, what does a 6 volt 1.5 watts filament lamp mean? If I just see if I can find a blank page somewhere to write on. Now, here we are. Actually, while I'm on this additional answer space page, it is worth using this rather than trying to sort of squash calculations under the bottom of the page or all around the text. Your working is more likely to be seen by the examiners. The examiners, all the exams you take are scanned in and then marked on screen by examiners. I've been doing it myself. Your work is more likely to be seen if you use the additional answer space. So use it, keep your work nice and clear, and write down your question number in the margin so it's clear which question links with what. Legend Footy says, what does 6 volt 1.5 watt filament lamp mean? So 6 volt 1.5 watt. Okay, so that's telling you the power rating and the voltage of the lamp. And all that means is that if you connect the lamp to a 6 volt supply, it will produce 1.5 watts of power. And from that information, so that's our power and that's our voltage. From that information, you could then find current, resistance, whatever you want, using the 3 power equations: P equals IV, P equals I squared R, P equals V squared over R. Remember, with these 3 equations, I do have a video actually about power dissipation on the YouTube channel. Remember that these 3 equations, you can use any of them. They all, in theory, work in every situation, but in practice, you need to choose the one that you can use based on the knowledge that you already have, the data that you have for the question. Fiery Life says, what's the V out equation for? That's the potential divider equation. So in a situation where you have a circuit like this, which is a potential divider, this is your V in. this is R1, this is R2, and you measure the voltage here with a voltmeter or a sensor of some sort, and this is V out. So you can use the equation that's on the formula sheet. V out equals V in multiplied by R2 divided by R1 plus R2. That's on the formula sheet to work it out. That's the potential divider equation. But potential dividers, really briefly, I do have a video on potential dividers as well. Check that out. R2, the voltage out is proportional to the resistance across it here. So you're dividing up this voltage by using two different sized resistors here. So a bigger resistor here will result in a bigger voltage out here. So usually one of these would be a variable resistor of some sort, or an LDR, or a thermistor. Yes, this will be a video after. I think YouTube's automatically going to upload this once I stop the recording. Monaco Super, I have no idea if it's going to be hard this year. But I mean, I know it's easy for me to say this. It doesn't matter too much if it's a difficult question for you. The most important thing is the spread of marks. They will adjust the grade boundaries based on how difficult it was. This was a difficult question last year. The grade boundaries were correspondingly high. I know my students last year actually did better in the 2014 electrons paper than they did in the 2014 mechanics paper. The difference between a de Broglie wavelength and a normal wavelength, essentially, a wavelength is for a wave. But what we can do is we can apply, if you find that if you accelerate anything to a high enough speed, for example, an electron, it will demonstrate wave-like behavior. The electron diffraction experiment shows that. So a wave each particle must also have a wavelength if it's traveling fast enough. You can use the de Broglie wavelength to work that out. Potential dividers are used as sensors. So this is, I've just explained the potential divider circuit here. As I said, there is a whole video on this for Viralite if you want more info. But they're usually used as sensors. The example in this exam paper we've just gone through is of one that's used to switch a light on and off. But you could use it. You could put a thermistor in place of R2 here, and as the temperature increases, the thermistor's resistance will decrease, and that will result in the output voltage decreasing as well. So it's essentially a way of turning a varying resistor into a voltage, which is ultimately what sensors and computers need to read our voltages. So a potential divider circuit is used as a sensor. Bergkamp 49, and it's not NTC thermistor. You just need to know that as the temperature goes up, the resistance goes down. You do need to know the wavelengths of the EM spectrum, Josh. You should know for each section. If you go on cowenphysics.com on the electrons, waves, and photons definitions page at the bottom there, I've got a summary of the different wavelengths. And yeah, sorry, Kester Bates, yeah, assume all thermistors are NTC. They won't throw anything else at you. Okay, I'm not able to add links into the comments box on this, but if you go to either youtube.com/cowenphysics and look at the playlists, there will be a playlist for electrons, waves, and photons. If you go on cowenphysics.com on the website, go to electrons, waves, and photons. At the top of the page there'll be a link to the walkthrough as well. You should be able to find it. Over 9,000 dude is saying V is proportional to R, correct? If current is constant, oh sorry, are you talking about potential divider equations? Yes, in a potential divider equation, even though the current is changing, we can say that V is proportional to R because it's the ratio between R1 and R2 that's important. So if R1 is staying the same and R2 is increasing in resistance, then the V out will increase as well. Just flicking through, see if I've missed any questions. I think. Okay, Abdul Ibrahim. My question is, what's the formula for terminal PD? Is always PD across all components in a circuit? Is that it? So the definition of terminal PD, it usually comes up when we're talking about internal resistance. So here's our cell, and that's our internal resistance for the cell, and we put a dash box around it. Terminal PD is what happens if you get a battery and you connect the voltmeter directly across the battery. So you measure, excuse me, if you measure the voltage here, that's terminal PD. Remember that if I connect a whole circuit here, so it's not enjoying this diagram, is it? If I connect a whole circuit up here, the voltage in every branch of the circuit is the same. So actually, the terminal PD is also the potential difference across this part here. How that differs from the EMF is going to be related to how many volts are lost by the internal resistance here. So you have the equation on the formula sheet: E equals V plus I little r, and little r is the internal resistance. So when the battery is not connected to anything at all, there's no current flowing. So the voltage that you measure on the battery is actually the EMF. But as soon as you put a load on the circuit and that current starts to flow, some volts will be lost in the internal resistance, and then the voltage will, the EMF will be higher than the terminal voltage. The terminal voltage will be lower. Monaco Super, I'm assuming you're referring, how do you get up and 0.8 amps? I'm assuming you're referring to the second question with the circuit there. The 0.08 amps calculated is because we know that the current at point X is 0.16 amps, and then part 3 of that question tells us that the current at X is twice the current at Y or Z. So we know the current flowing through Y and Z is half that, so that's the 0.08. Internal resistance. Fiery Life has asked a question about internal resistance. Will the resistance of the cell battery suffice as a definition? Have a look at the mark scheme for this paper here, which had the definition of internal resistance. It's a tricky one. I think I've put the same definition onto cowenphysics.com. It's you need to talk about energy being lost or lost volts. I think for a good definition. Monaco Super, not all thermistors are NTC. NTC means negative temperature coefficient. There are positive ones as well. Most thermistors are NTC, and most importantly, the only ones you need to know about in the OCR specification are NTC. So if you see a thermistor, it will be an NTC. Spectral lines, EDC spectral lines, evidence for the existence of discrete energy levels. They show that the electron, the spectral lines are photons of very specific frequencies, very specific energies. They can only be emitted at those frequencies. So if there was a different mechanism going on in the atom, then we would see photons being emitted from all frequencies, but instead we just see them from very specific ones that correspond to the electron energy levels. So a photon's only emitted when an electron moves from one energy level to another, and that energy level corresponds to the energy of the photon, which corresponds to its color. So we get the discrete colors. Yeah, Monaco super. When T increases, resistance decreases. The LDR is the same effect. When the light intensity increases, the resistance decreases. If you've got any more questions, feel free to add them. I'll keep on. I'll stay on for a few more minutes. Lee Sutton, there are a few practicals that come up in the spec that you need to describe. Determining Planck's constant with LEDs is the one where you look at what voltage allows an electron, sorry, what voltage allows an LED to conduct to produce light. So have a look, refer back to your textbook for that. First of all, refer to the spec for which specific practicals you need to know about. Refer to the textbook for that, because you could be asked to describe them. A common one to describe is the photoelectric effect one as well. Be sure you know what you're doing with that. Looking back to the mechanics paper you did last week, a couple of weeks ago, there was a question in that where you had to describe a practical, and often you might be asked to state the equipment you're using and what you're measuring with that equipment. So it's really important that you state both the equipment and the quantity you're measuring. If you miss one out, you're not going to get any marks for it. Z33EEs, yes, no, you don't have to memorize the frequencies of waves on the EM spectrum. You should instead memorize the wavelengths. If you get asked about the frequencies, you can convert one to the other using the formula C equals F lambda. The difference in a progressive wave and a stationary wave, a couple of people have answered it in the comments. A progressive wave carries energy from one place to another. A stationary wave doesn't. It stores energy in pockets. Any more questions? Okay, what is meant by the electrons of an atom being excited? So two ways to excite an atom, the electrons of an atom. I think burning probably does it. But more commonly, passing electricity through a gas will excite the electrons. Or not just a gas, actually, solids I think too. But a good example is a fluorescent tube, a fluorescent lamp. an energy-saving light bulb, if you pass electricity through that gas, it causes the electrons to become excited. The electrons jump up in energy level, then they relax back to the ground state, and it's that point when they relax back to the ground state where they release a photon. How would you explain the difference between a transverse wave and a longitudinal wave? A transverse wave is a wave in which the oscillations are perpendicular to the direction of travel. That's a transverse wave. And a longitudinal wave is one in which the oscillations are in the same direction as the direction of travel of the wave. Mason Hoth, one property of EM waves that distinguishes them from all of the waves. There actually was a question in this paper. I don't know if you've just joined us. There was a question in this paper about that. The best answers to write down are they can travel at the speed of light in a vacuum and that they travel in a vacuum. Z33 EEs, don't worry about radians. You can, I don't think, at AS, I don't think you'd be required to know them. I know in A2 you will use radians once you do circular motion. Phase and path difference. Phase difference you can work in degrees for. Path difference, you work in fractions of a wavelength. So for neither of those do you actually have to use radians. In fact, you're probably better off not doing. Yeah, Z33E is a radian is just another unit for measuring angles. 360 degrees is 2 pi, so 180 degrees is pi, and so on. You can fraction it up like that, but don't worry about that. Path difference and phase difference is a subtle difference. The phase difference is the difference measured in degrees between 2 points on a wave, whereas path difference is describing 2 waves when they arrive. What proportion of a full wavelength are they out of phase by? So you could, it's a very subtle difference, but you would basically you would measure phase difference in degrees. You would measure path difference in fractions of a wavelength. I is directly proportional to a squared. The intensity of radiation is proportional to the square of the amplitude of that radiation. So in the question we did earlier, it's reflecting the fact that while one of the waves was 3 times higher in amplitude, it would be 9 times higher, 3 squared times higher in intensity because of that relationship. It's quite a small part of the spec, but it's just useful to have in mind. How do you know which dimensions to use for the cross-sectional area? That's a really good question. If I go back to my blank page here, I mean, for a normal cable, it should be fairly obvious that this is your cross-sectional area here. So pi r squared. The only thing to be careful of here, they are more likely to give you the diameter of the cable than the radius. So it's going to be pi d squared over 4, or you halve d and feed it in as r. For a rectangular cross section, something like you had earlier in this paper, the current, let's say the current is flowing along that way along the wire. and out of this side. That is our length, okay? That will be the length of our conductor. Which means the cross-sectional area, cross-sectional area is the area I'm shading here. So that's going to be the thickness there, or the height, multiplied by that width there. Really, really important that you choose the right dimensions there, because it will cost you not just 1 mark, probably all the marks for that question if you were to mess up which dimensions you choose. So it's the cross-sectional area is the cutting across perpendicular to where the current's flowing. It's that area there. Why do the electrons produce circular diffraction patterns? That's a really good question. It's because rather than just passing through 2 slits, as in the Young double slit experiment with light, instead they're passing through a grid, a lattice of atoms. You're using graphite atoms as the slits, and you haven't just got single slits. You've got sort of slits in every direction there, because it's a grid, and the result of that is it produces a circular diffraction pattern. Okay, I've got about 1 minute, and I'm going to sign off at 9 o'clock. You guys need to get a good night's sleep. So, last question. Which pattern does a single slit produce? It produces, it doesn't produce fringes in the same way as the Young double slit experiment. It will produce a diffraction pattern. There will be diffraction, but there won't be interference. Okay, thank you everybody for tuning in. Good luck tomorrow. From the quality of the questions I've been seeing from you all, you've got a really good idea of what you should know, and a decent experiment. Really last answer, Josh Curtis, you do need to know the differences between UVA, UVB, and UVC. Have a look in your textbook for the details. I can't recall actually seeing a question that ever asks that, so it's probably 1 or 2 marks in the paper at all if it comes up. But yeah, okay. Thank you very much for tuning in. Bye.